Hello students, so welcome to class 8. Okay, so we have started the synthesis part, okay, of the cyclopentadienyl, and some synthesis we have taken. So we learned regarding this ferrocene. This was first stated in 1951. Okay, 1951 1952 by Miller Pawson Miller Pawson KD, KEEDY, KD, okay, Muller Pawson, KD 1952. Okay, so this was where it was accidentally found ferrocene. So when he was using this Grignard's reagent MgBr, take it as H here, okay, and treating with iron oxides, okay, so iron oxide and this compound, and he got this compound, okay, like this was the compound he observed. Okay, this is what they used to find. It's called fulvene, okay, FULL, fulvene compound. So this was expected by this Muller Pawson KD. So by taking this Grignard's reagent and they treated with iron oxide here, and they expected this compound, but fortunately what happened, instead of this fulvene, they got this compound. Okay, so they got this compound here, Fe, and like this. So this was the compound they observed, and this is called your ferrocene. This is was your ferrocene, like this. Okay, so this is how the first preparation of the ferrocene by Miller and Pawson was been defended. Okay, so depending on the sigma bond formed by this metal and pi interaction, okay, so there were different structural elucidation of this ferrocene here, and you can see that later on it came with the sandwich structure given by Wilkinson, Woodward and Fisher. Okay, so in the previous this one I have shown you Wilkinson, Woodward. Okay, so they were the first person to give this sandwich structure, okay, of the ferrocene. Okay, Fe, so like this. So this was a sandwich structure given by the Wilkinson. Okay, Wilkinson was the first person to show this structure depending on the sigma and pi bonded and IR X-ray diffraction methods, magnetic properties, chemical properties. So depending on all this, so sandwich structure and double cone structure was discussed by Fisher. So this was Wilkinson, and double cone structure, something like that. This is a cone they used to show in this way. Okay, 1 2 3 4 5, like this, something like that. Okay, so this was something like that. So cone they used to like this, something like that. Okay, like that. So double cone system. So this is a cone. So double cone system. This was given by Fisher, like this, Fisher, Wilkinson. So they used this type of structures for this ferrocene compound. Okay, depending on the IR studies, X-ray studies, magnetic properties and all other things. Okay, and later on after this there was thallium also, cyclopentadienyl. Okay, thallium cyclopentadienyl was prepared, but thallium was toxic in nature. Okay, thallium was toxic in nature, and that's why this was discarded. So later the chemistry went on, then lithium cyclopentadienyl metallocene was prepared. Okay, so like this it will go on, but one main thing is what your ferrocene, say it is ruling the market, ferrocene. Okay, so it was also prepared later on by taking FeCl3 in powder form. Okay, so ferric chloride in the powder form, and this was treated in the presence of triethylamine, Et3N, triethylamine, Et3N. Okay, this was it was treated and it was refluxed. It was refluxed. Okay, so this was been done, and here triethylamine was used here. So sometimes they will ask, so it is used to remove the HCl. Okay, since it is a base, so during this reaction, reflux reaction with FeCl3, so powder and this, so what happened, there was a generation of HCl, and to remove this triethylamine was used. Okay, so to reduce to remove the HCl. Okay, and the powder it was used to reduce powder. This FeCl3 powder was used to reduce Fe plus 3 to Fe plus 2 finally. So reduction. So finely powdered iron was also acting as a reduction here. So which was reducing this Fe plus 3 to Fe plus 2. Okay, so this was the alternate synthesis of the synthesis of this ferrocene by using the triethylamine. So overall, if I want to give, so we can give like this: FeCl3 plus Et3n, okay, dot HCl. Okay, so reflux, to reflux it in the in catalyst, in the presence of catalyst and at high temperature. Okay, in the presence of catalyst and high temperature, so you get your ferrocene. So FeCl3 plus triethylamine dot HCl in refluxing and the presence of catalyst and high temperature, so you are going to get your ferrocene. Okay, this is what. Okay, so this is what about the ferrocene history, is it? So like this, even cracking process also it is possible by cyclopentadiene preparation. So sometimes how to the cyclopentadiene preparation. So how this cyclopentadiene is prepared. So actually, while going for this synthesis, it is prepared freshly. Okay, cyclopentadiene by cracking process. So by C10H12. Okay, so this was deca carbon. This was taken, and after cracking this process, CRACK, and the cracking process, so you get here C5H 6 twice. Okay, so this was the how the cyclopentadiene was being utilized, how was being freshly prepared by cracking process. Okay, C10H12. So cracking process, you get the C5H6 anion. Okay, so twice. So you get this cyclopentadiene too. Okay, so this is what about the small history of what you say this ferrocene. Okay, now we will go for some of the reactions, because ferrocene we call it as what, highly aromatic in nature. So they will ask some reactions to prove why this ferrocene is highly electronegative in, sorry, if aromatic in nature. So there are different reactions we can show for this to show that ferrocene is highly aromatic in nature. So one by one we will show, because as benzene is showing some of the very important reactions, same thing ferrocene also show, like electrophilic substitution reaction. Okay, electrophilic substitution reaction. So this is what even there are some different reactions shown: nitration reaction, halogenation, carboxylation, sulfonation, Friedel-Claps alkylation, acylation, Wittig's reaction. These all things, these all reactions can be shown by ferrocene also, so which is shown by the benzene, and that's why this ferrocene also called as inorganic, sometimes benzene. Okay, so if you see this hydrogenation and de-Alders reaction, so usually they are not shown by ferrocene, which is a common reaction usually shown by the dienes. Okay, so this shows that the ferrocene is highly aromatic in nature, and hence they and that's, so this also is the possibility, because usually hydrogenation, okay, hydrogenation and Diels-Alder reactions here. So this is very much important: hydrogenation and Diels-Alder reaction. Okay, so usually they are the common reactions shown by the dienes, as we have seen in butadienes and cyclobutadienes. So we have seen that in cyclobutadiene or butadiene, they are going to form the dimer with the help of Diels-Alder's reaction and even hydrogenation reactions. But this is not shown by ferrocene. Okay, usually ferrocene is not showing these reactions, only dienes are showing it. So that shows that ferrocene also is a very quite acting as a very good aromatic in nature. Okay, now we'll see like benzene also. So benzene is not going to show, and so the ferrocene also is not going to show such reactions, and that's why that is a proof of the aromaticity of the ferrocene. Now if you go for electrophilic substitution reaction, so when you take this ferrocene, so simple, you can take this ferrocene Fe like this. Okay, and if you treat this with electrophile, what will happen? Now you are going to get this intermediate. First you are going to get this iron is in 2 state like this, and here you can see that first this is a state where the electrophile is going to interact with this, followed by the intermediate here, and you get this intermediate like this. Okay, here iron is there, and this as usual will be there here, and here you can see one proton and electrophile is attached here in this way. Okay, and now what will happen? Next step, to gain the aromaticity, this will give the electron and go away, and you are going to get this compound. So you are going to get this compound. like this. So you are going to get this compound. So here we can get it here E. So electrophile is going to attach it here, and this hydrogen will go in the form of proton, like H plus. So like this we are going to get this reaction, electrophilic reaction. So here electrophile is attached here in this position, like okay. So like this electrophilic substitution reaction takes place. So initially it is going to interact with the iron center, and later on it is going to interact with the second position here of carbon here. This is bond is broken here, or it is going to change in this way, and here we can see to again it will to gain the total neta phi conditions. What will happen here? So you are going to see that this proton is released here in the form of H plus, and the aromaticity of neta phi is going to generate here, and you are going to get here ferrocene as if, and this electron is going to be substituted here from the one proton here. So like this. So this type of reaction is called electrophilic substitution reaction, electrophilic substitution reaction, and this is going to happen usually shown by the benzene, okay, and that's why you can see that this reaction is also shown by the ferrocene. So this is one proof that why ferrocene is acting as a aromatic in nature, okay. So this is what you can mention here, that the E plus electrophile is going to interact with the metal, okay. So they are going to form first cationic structure that I have shown here. So interact with the metal, and they are going to form some cationic type of center here, diene, okay, forming cationic diene intermediate, okay. Later it loses the H plus ion, later it loses the H plus ion, okay. So I have shown it here. Later it loses the H plus ion here, and it is going to substitute the electrophile. So this is how you can explain with the reaction, with this reaction. Next one is nitration. So you can go for the nitration reaction also, second reaction. This also you can show. So direct nitration of ferrocene is not possible. If you take ferrocene and try to direct nitration, so it is not possible, okay. So it will be chapped. So it has to be done indirectly now. So how it can be done indirectly? Because you know that if I take this ferrocene like this, okay, if I take this ferrocene and we treat with the concentrated HNO3, so what will happen? It will oxidize, you know. So this is going to form like this and like this, and it is going to form in this like this, okay. So blue in color. So this is going to be formed instead of nitration. You are going to find this, okay. This is going to be oxidized directly. So that's why ferrocene cannot be direct nitration cannot be done for the ferrocene. Instead, indirect way it is been done, okay. So that is what. So 17 electrons is going to form the cationic ferrocene here. So this is what your cationic ferrocene, which is 17 electron species, which is blue in color. So this is blue color species, which is 17 electron, and blue in color, and it's a solid, you know, in a highly unstable form also. So this highly unstable also. So that's why this is not possible actually, okay. So that's why indirect way we are going to see. So indirect. So because if they ask the questions why, then you can give this reason. Now indirectly way how they can give. So how we can go? So you take this ferrocene like this, okay. So take the ferrocene, and this is treated with butyl lithium first. This is very important. So when you treat this with butyl lithium, so what is going to form? So you get this compound. So you are going to get lithium substituted this ferrocene. Then you treat with N2O4, okay. This is a compound, and now you are going to get the compound, required compound, that is your ferrocene, and you get here nitro like this. So you are going to get nitration here. So N2O4, this is a reagent, very much important, okay. N2O4 dinitrogen tetroxide. So this is what used, okay. Instead of HNO3 strong, so we are going to use this N2O4 as a nitrating reagent in this case, okay. Otherwise this is going to happen, which is not stable. So this is what happens. So butyl lithium is then the lithiated ferrocene is going to get. From this lithiated substitutes ferrocene, you are going to treat with sodium nitrogen tetroxide, and we are going to get this nitrated form of ferrocene. So this is also is a good nitration, as benzene shows. This also we can do it. Next is what? Sulfonation. This also is very much important, third one, okay. Sulfonation. Similarly in sulfonation you can see that, so this ferrocene, you can take this, or you can take anything, you can take like this Fe ferrocene. Now when this is treated with sulfonating, means what? Concentrated H2SO4, okay. Concentrated sulfuric acid in the presence of acetic acid AC2O. Okay, AC2 means what? CH3COH, acetic acid, and chlorosulfonic acid, ClSO3H. If you do this, so you are going to get this compound initially like this. So you are going to get this SO3H. This is what sulfonation. Okay, so this is AC2O, acetic anhydride. Okay, so this is your in the presence of acetic anhydride. AC2O, this is nothing but acetic anhydride, concentrated sulfuric acid, and chlorosulfonic acid, ClSO3H. So if you do this intermediate and treat this ferrocene here, so you are going to get this sulfonated ferrocene. So this is what sulfonated ferrocene. This type of sulfonation can be shown by the ferrocene. So which is also structure of what? The benzene, which is also a very characteristic reaction by the benzene. So this is also this type of reaction is also shown by the ferrocene. That's why it's also called as a aromatic in nature as a benzene. Next is what? Halogenation. So you can give the fourth reaction, that is halogenation. See, okay, in the best halogenation done here is bromination, as benzene does. So same thing our ferrocene does, where I will take it as a ferrocene here, simple, and this is first treated with alkoxide. Okay, bromine alkoxide, and hydrolysis is done here. When you do the hydrolysis, what will happen? You get this first compound here, iron, like this. So BOH twice. Okay, OR is there here, OR twice, you can take it here. Okay, then this produces HgCl2. Okay, then this is treated with the HgCl2. When you treat this HgCl2, what I am going to get? I am going to get this compound. If we like this, I am going to get this compound. Okay, so this part is been relieved, OR2, and we get what? HgCl now here. Now this what I am going to do, treat with bromine now. Now when I treat this with bromine, I am going to get my this compound, bromination. See here, like this. So this is how the bromination. So first you take ferrocene. See this you have to remember. Okay, this is the expected answers to be written in the examination. So what reagents we are taking? So halogenation. So take this ferrocene, then dialkoxy boron you treat with this. Okay, hydrolysis. So this compound will learn. This is a very easy releasing group here. So now you treat with this HgCl2. Okay, mercury chloride. Now what will happen? This HgCl will easily substitute this. Okay, alkoxide. Now what you do? Now you treat this with easily bromine, and then you will get the bromine substituted ferrocene. So this is a process of the bromination. Okay, and these all substituents are used only for the proper bromination. Direct bromination is not good. So again, as concentrated nitric acid I said, so it is going to have the negative effect on the ferrocene. So similarly, so directly you cannot. This is what the researched reactions done on the ferrocene. So before that you have to treat with this, then with this HgCl2. Okay, and because which is a very reducing agent, very good reducing agent. So this will easily remove. It will substitute here, leaving this group here out, and this is going to substitute here, and later on when bromination is done, so totally this also is very good leaving group. It will go out, and bromine will go, substitute here. So this is what about the bromination. Okay, so here as such we don't require any mechanism here. It's very simple. So you can think of the odd mechanism also related to organic, but that is not required here in this case. Just you show the reactions to confirm, to say or to prove that your this ferrocene is a very good organic in nature, aromatic in nature. So one more thing as carboxylation. Okay, one more fifth reaction is shown, carboxylation reaction. This also can be confirmed here, as benzene shows carboxylation. So here also same thing, you take your ferrocene here like this. Okay, and you treat with butyl lithium, same thing here. So after treating this butyl lithium, what will happen? You find this compound lithium, as we did here, substituted lithium is going to find here, and then you treat with your carbon dioxide. Okay, in the presence acidification, and you get your carboxylation like this. Okay, you get your carboxylic acid like this, CO2H. So this is what about the carboxylation. See here. So ferrocene you take, butyl lithium, then lithiated ferrocene, then carbon dioxide, hydrolysis, acidification, you get this one. So this is how carboxylation reaction is shown by your by the ferrocene. So this also is a very best example of aromatic in nature, say carboxylation reaction. Even next we'll go for sixth reaction to confirm our ferrocene is aromatic in nature, that is Friedel-Crafts acylation. Friedel-Crafts acylation. So this also, as in organic chemistry we learn, similarly we can do it here again, same thing. We can go for your ferrocene, okay, and you know that what we do for acylation. So we take CH3COCl. so this is what, in the presence of catalyst AlCl3 CH3COCl, this is what acetyl chloride we take it here, and aluminum chloride we use it here, and we are going to get here this compound. Okay, so we are going to get your first this compound, that is your C double bond O CH3. Okay, now if you take excess of CH3COCl, so you are ending up with this compound, iron, like this. All the signs COCH3, here also COCH3, so like this, plus AlCl3 plus H plus or H2O or H plus, something like that. Okay, so this is how we can show the acylation reaction. See, ferrocene is there here, then you treat with acetyl chloride CH3COCl in the presence of catalyst AlCl3. So what is going to happen here? You are going to get this compound where this substitution takes place, monoacylated compound ferrocene is going to get. Now if you take this in excess form here, so this one, so what we are going to end up, excess of this one, so we are going to get this disubstituted COCH3 so like this. So like this you can see that Friedel-Crafts acylation reaction is shown by your ferrocene, and that is also very good aromatic in nature. Similarly, when acylation is there, next is what, Friedel-Crafts alkylation. So this also will complete alkylation. Okay, so what is this Friedel-Crafts alkylation? So similarly, same thing, you can start with your ferrocene like this, and alkylation what you do, so you treat with what, alkenes, CH2 double bond CH2 in the presence of again catalyst, that is AlCl3 at around 100 degrees centigrade and around 230 atmosphere. This condition is very much important here for alkylation. So ferrocene and alkenes, you take AlCl3 100 degrees centigrade temperature and in 230 atmosphere pressure. So what you are going to get, you are going to get this compound like this. So CH2 CH3, this is what, okay, you are going to get CH2 CH3. Now same thing here, if you take this excess here, okay, of CH2 double bond CH2, if alkene, if you take this excess, you are going to end up with your this compound like this, and you are going to get both way CH2 CH3, and here also CH2 CH3 like this. So you are going to get this substitute. Okay, ferrocene you take, you treat with this alkenes, AlCl3 100 degree centigrade 230 atmosphere, you get mono substituted alkyl ferrocene. Now if you take this excess of this monomer here, so the ligand, ligand here or intermediate here, so what will happen, you get disubstitute as you got in acylation, same thing you get here. So like this, these are some of the reactions. This is alkylation, acylation reactions, nitration, sulfonation. All these reactions will confirm that the ferrocene is highly aromatic in nature. But this is a simple reaction shown by the benzene and shown by the ferrocene also. But there are two more reactions which is not shown by benzene, okay, but it is shown by ferrocene. See here, in the next video we'll go for the such reactions which is not shown by benzene. Benzene fails to show that reaction, but ferrocene does it very good. Okay, there are two reactions, and that will confirm that ferrocene is highly aromatic than benzene also. That is what the fascinating here. So that will confirm that ferrocene is more aromatic in nature than the benzene. So this is how. So in next video we will go for which are the reaction, which are these two reactions which will confirm high aromatic nature than benzene. That we'll learn in the next video. Thank you.